Greetings everybody. Let's take a look at basis and dimensions for vector spaces. So if we got the vectors v1 up to vn, and these things form a basis if and only if the span of those vectors gives us the entire vector space, and our v1 up to vn are linearly independent. So a theorem that we get from that, from this, is that if v1 up to vn and w1 up to w sub m are bases for this vector space v, then the number of elements in that basis are going to be equal. And now this is a little bit involved, but it's kind of ends up being a big deal because this is really going to tell us that our notion of dimension is really well defined. So let's look at the proof of how that might go. So suppose that our two sizes are different, that n is not equal to m. Then without loss of generality, let's say that n is going to be less than m. So since our set w sub I form a basis, then for each one of our vectors in our other set, we can represent that as a linear combination. So v1 looks like c sub 1 up to j, so here's our linear combination for v sub 1, our linear combination for v sub 2 in terms of the w sub j will represent like this. Our subscript on those coefficients is really the coefficient for our vector, or our index for our vector, and our superscript then is just one for telling us which vector in our w set that we're summing over. So our v sub n then looks like this as a linear combination of the w sub j. So we take the v's, we represent those as linear combinations of the w's. But then also because the v sub I form a basis as well, then we can take w sub n plus 1. So we said that m was going to be bigger than n, so there is a w sub n plus 1 in there. And we can represent that as a linear combination of the v sub I, because the v sub I form a basis. So if we take all of these and kind of substitute them back in for the expressions that we just had, then we can write our v sub i's as linear combinations of the w's. We kind of redistribute our d sub i's, rearrange terms, kind of group things together, and so we end up with these, our linear combination of w sub n plus 1 in terms of the other w, in terms of all of the w's that we have. So kind of performing the same trick, if we kind of subtract things over on one side, then this gives us a linear combination of the w sub I that is 0. Okay, well, since the wi form a basis, this means that the only way this can happen is for all of the coefficients to be 0. So this gives us a system of equations. So we've got our coefficients for all of the w sub k's that are not n plus 1, and then we've got the one for w sub n plus 1. So all of those are 0, and this one has to be 1. So we look at that, take those first n plus 1 equations and look at them in matrix form, then we get a matrix that basically looks something like this. Okay, so we can write it like this, times our vector d sub 1, d sub 2 up to d sub n, and that's going to give us our result vector. So now what we want to do is, for that matrix C, let's think about the reduction to reduced row echelon form. Okay, so we've got this, what do we have? We've got a total of n plus 1 rows. We've got a total of n columns. And so when we reduce that thing to reduced row echelon form, just a couple of things can happen. So one of those is that we reduce it to row echelon form. We've got the identity matrix, and then we've got a row of zeros along the bottom. Or we reduce it to reduced row echelon form. We've got this kind of identity matrix, and then we've got some zeros along the main diagonal, and then whatever our last row happens to look like. Well, if we were in the first case, then what does that mean? If it reduced to this, so we've got ones along the main diagonal and zeros there, then it means that it's, in particular, if we look at this last component, there's no way, since those are all zeros, that we can multiply those together to get 1. So that's just not going to happen because all of our rows in there are zeros. And so what this means is that we can't really have a solution to our system that we're supposed to have. Well, since that can't happen, what this really means is that we must be in case 2. Okay, so for the second case, we've got ones along the main diagonal and zeros the rest of the way down. But what happens there, so if we kind of forget about that last row for a second, then what that gives us is a non-trivial solution to this system where we're only taking like the first n equations. So we've got a non-trivial solution to that system. And so what that also means is that we've got a non-trivial solution to the c sub ij's that we were looking at times some vector is going to give us the matrix of zeros. Well, if we go back a couple of steps, then if we take that solution, that non-trivial solution, so non-trivial means some of these e to the i's are going to be non-zero. So if we take the linear combination of those times our v sub i's, while doing our rearrangement back to our w's, this is really our matrix times, so if we kind of rearrange things, that's our matrix times this e sub I. Well, these e sub i's give us 0 in all of those. And so that gives us 0 times w sub i's gives us all zeros. Now we've got a linear combination, a non-trivial linear combination of the v sub i's that gives us 0. Well, that contradicts the linear independence of our collection v sub i's. So now we've kind of gone through these logical deductions. Each time it leads us to a contradiction, and since it does that, the only thing that we can conclude was our original assumption that n not being equal to m is actually impossible. And so what that gives us is that n is equal to m, and therefore all bases that we pick for this vector space V have to have the same cardinality when we're talking about finite dimensional spaces. So kind of the conclusion that we get from this is that this notion of dimension, and dimension really being defined as the cardinality of a cardinality, finite cardinality. We're not dealing with anything with infinite dimensional vector spaces at this point. So the finite cardinality of a basis is going to be the same regardless of what the basis is. And so this dimension, this notion of dimension, does make sense. It is going to be well defined for finite dimensional vector spaces. So from this, we've kind of gone all the way through talking about bases and linear independence and getting to this notion of dimension being solid and concrete. So I hope you've enjoyed this, and we'll pick it up in the next video next time. See you guys then.